For image processing, we need to get the raw video data to a series of images that can be trackable. And here's a summary of the image processing workflow. So the camera took 30 color frames per second, and each frame consists of a red, a green, and a blue layer. So then we split each frame into those 3 layers, and for each of these layers we removed the salt and pepper noise with a small diameter Gaussian filter, and then we did background correction by subtracting the image with a larger diameter Gaussian filter. This gave us a background corrected image that we need to further sharpen. So the first step was to create a blurred image of this using a Gaussian filter of about 20 pixel radius and subtract this from the corrected image, which reduces the background around each particle. And then we smoothed that over using a smaller diameter Gaussian filter of about 30 pixels in radius, and we did this process 3 times, and this sharpened the image to get rid of noise from the CMOS sensor. Then we calculated the 99th percentile, the pixel intensity, and we removed any pixels lower than 99th percentile. So anything above the signal gets turned to a 1, and anything below this cutoff gets turned to a 0. And this gave us a binary image of 1s and 0s for the red, green, and blue layers. Then we overlapped the 3 layers, and only if all 3 pixels were 1s did the final image have a 1 signal coming through. Here's a false color view of the resulting recombined image. Only the white parts are retained, and you can see the red, green, and blue parts that are coming through some frames, and those will be deleted. Also, the purple, yellow, and cyan parts will be deleted because they're a combination of 2 of the different layers. Here's a few seconds of what the final frame looked like for one of the movies. For each of the images, we used a function that provides the centroid of the blob and the areas and pixels of the blob. This gives us a table for each frame, and here's what the data looks like if it's animated frame by frame. And looking at this as animating, you can clearly see what looks like the particles, but we also see some random bits that are basically noise, so we need to get rid of that with a tracking algorithm. Next is generating tracks from this data. So in order to do that, we assumed each blob in frame 1 was a trackable particle located at x0 and y0. Then we advanced 1 frame and calculated the x and y distances between that x0 and y0 in the previous frame and all the other particles in the current frame using the Pythagorean theorem. And the closest blob in the current frame was linked to the blob of the previous frame. We could improve this further by using an area matching the blob in the previous frame to the blob in the current frame to make sure we were assigning the tracks accurately. But we found that with good initial image processing, we had dozens of particles that were easily tracked. For those particles that we couldn't find a match within 10 pixels for 10 frames, we dropped tracking those in subsequent frames. We could add the ability to track new particles as they drift into the field of view or the focus, but we had a few dozen particles of data, so we didn't try to do this. The result is a table where each row is unique particle track. We created some statistics for these tracks, like number of steps in the tracking data, the average area in pixels, and the conversion to radius in micrometers. As a quick visibility check, you can visualize the trajectories of the particles by putting them all at the origin. You can calculate the total distance traveled in each step in the x and y direction, and although the particles are moving in very different trajectories, the total distance they have traveled in the x or y axis is remarkably consistent. Next, we had to calculate the mean square displacement, or MSD. MSD is the key value measured experimentally needed for Einstein's equation. To get the MSD, we took the entire track of each particle, then calculated the difference in x or y coordinate from frame to frame, squared this, and then took the average of it. The x and y MSD were calculated separately. Sometimes the particle drift in x or y coordinates because the slide might not have been closed on the side, or some liquid was diffusing out, or the UV LED light was heating one slide. We tried to be very careful with slide preparation to minimize this effect. Wrap the sides of the slide with saran wrap and turn off the equipment to let it cool to equilibrium room temperature, and then performed a 60-second recording. You can see in the other video how we calibrated the camera to convert pixels to micrometers, and also the unit analysis we did to make sure to pick the right ideal gas constant. Then we had to do the actual calculation, which had several large numbers in it. We calculated this for each particle to get the average value for Avogadro's number.